Euclid's Elements, Book 1, Prop 29. A straight line falling on two parallel lines makes the alternate angles equal to one another. The exterior angle equal to the opposite interior angle, and the two interior angles on the same side equal to two right angles. Now, this prop is the converse of props 27 and 28. Remember there we started with equality of angles and we proved parallel lines. Well, now we're going to start with parallel lines and prove the equality of these various angles. So let's start with two parallel lines, A, B, C, D, and it's given that they're parallel. This is my sign for parallel. So here's our given. AB is parallel to CD. We're going to prove three things. The first thing is we're going to prove, if the line falls on a line, we're going to prove that the alternate angles are equal. So particularly we're going to prove that this angle here and this angle here in blue are equal. The second thing we're going to prove, so we'll call this angle 1 and angle 2. So we're going to prove that angle 1 equals angle 2. The second thing we're going to prove is that the exterior angle and is equal to the opposite interior angle. In this case, we're going to prove that angle 3 is equal to angle 2. And the third thing we're going to prove is, let me get a different color angle here. We're going to prove that this angle here in red, we'll call this angle 4, and angle 2, the same side interior angles, when added together, equal two right angles. So same side interior angles added together equal two right angles. So in this case, we're going to prove that angle 4 plus angle 2 is equal to two right angles. So we're first going to start with a claim and then use Euclid's famous proof by contradiction. First, I'm going to say that angle 1 is equal to angle 2, that the alternate angles are equal to each other. If they're not, if they're not equal, then they are unequal. All right, that makes sense. And if they're unequal, one of them is larger. So let's assume that angle 1 is larger than angle 2. Well, let's add then this common angle, angle 4, to both sides. And what we get is, preserves our inequality, and we get the combination of angle 1, angle 4, is greater than the combination of angle 2, angle 4. But when we look at angle 1 and angle 4, we see that it's a straight angle. Namely, there's a line set up on a line, and it makes these two angles taken together equal to two right angles. This is prop 13. Well, if this is two right angles and it's greater than this, then this combination of angles must be less. So these angles must be less than two right angles. But if 4 and 2 are less than two right angles, postulate 5 tells us that when you have the situation, two lines with a line falling on it making the same side interior angles less than two right angles, then those lines, when extended, will meet. Therefore, we know that if we extend AB and CD indefinitely, they will meet. Well, the problem with that is that that's contrary to our given, that A and B are parallel, which by definition means they will never meet. So they can't meet. Therefore, that's our contradiction, and so the assumption that gave rise to this has to be rejected. Well, here's our assumption, that these lines are unequal. Therefore, we must reject that, and if they're not unequal, then they are equal. And so that's the first thing that we can prove. The second thing follows from this pretty easily. If 1 and 2 are equal to each other, we know that angle 3 is equal to angle 1 because they're vertical angles. Prop 15 tells us that. Vertical angles are equal. And we know that, so 3 equals 1, and we already proved earlier that 2 equals angle 1. Two things equal to the same thing are equal to each other, therefore angle 3 equals angle 2. The exterior angle equals the opposite interior angle. And that is the second thing we were given to prove. Finally, the third thing we want to prove is that the combination of these two has to be equal to 2 right angles. So again, we already know that angle 1 is equal to angle 2. And so we're going to, as before, we're going to add angle 4 to both sides. That's going to preserve our equality. Equals added to equals is equals. So the combination of angle 1, angle 4 is equal to the combination of angle 2 and angle 4. But as we said before, this is a straight angle. So this is equal to 2 right angles. Prop 13. Which means, since it's equal to this, this is equal to 2 right angles. And that's what we're trying to prove, that the combination of angle 4 and 2 is equal to 2 right angles. That the same side interior angles on parallel lines are equal to 2 right angles. Therefore, when we have parallel lines and a line fall on them, it makes alternate angles equal, the exterior angle equal to the opposite interior angle, and the two same side interior angles equal to 2 right angles. Since we have proved it, we conclude our proof. QED.